Yeah. Hello, everyone. I'm happy to give the second talk today. Yeah, I'm Gregor, and want to show some of the projects we did in the medical domain over the last years. And yeah, it's more or less like an overview of all of the projects we did related to IR and AI. So I think it's a good fit to this meetup. Yeah, so the structure of my talk. First, I want to give you a little bit of an introduction about how we can use IR and AI for data-driven healthcare, and motivate the case studies I will present. And then these are the two projects that are the main part of the talk. So first of all, we will look into an approach to how we can predict outbreaks of bacteria in hospitals by using structured data, more traditional machine learning approaches, and then we will look at another case study that is more information retrieval and also on the application unstructured data, and this is called MetNuggetizer, and we'll go into more detail about that later. And in the end, I will present the conclusion and also, like, of course, the take-home messages for you in only one slide, but to give like summary of this presentation. Yeah, so let's start with the introduction. I mean, to start with data-driven healthcare, we of course need data. That's the first problem. And in theory, there's a lot of data available. The main problem usually is if you're not associated with a hospital, you will have problems to access that data. But healthcare generates massive amounts of data. So I mean, that's very good if you want to perform that data-driven healthcare. So the first type of data that hospitals and healthcare in general is producing is structured data. So for example, here is a screenshot of the ICD coding schema, which is used to, log diagnosis, stuff like that. And that is very structured. So you have a hierarchical structure, and also codes are mapped to diseases. And we also, of course, have all the data categories that are collected in hospitals. So for example, the procedures, the blood test results, microbiological results, also the rooms and the wards and the organizational units that patients are located in. So that's all very structured. And we can say this is the first pillar of the data that we have in healthcare. Of course, there's also another pillar, which is more unstructured data. And I also have a few examples for that data type here. So, of course, everything that is related to medical publications that you can find on PubMed, for example. And of course, we also have guidelines that give medical professionals recommendations for how to treat specific diseases. And we also have other types of unstructured data like clinical notes or discharge notes. So mainly textual data, we can say. And to summarize, these are our two pillars of data that we can use for our data-driven healthcare approaches. And again, some of the examples I already introduced to you. And our goal is now we want to use methods of AI and IR to first of all support the clinical decision making, and the ultimate goal would be to improve the patient safety by using these methods that we have. And what I want to do now is present these two case studies that I mentioned to you. And the first one is on outbreak prediction. There's a lot of text, but I think it's important to give you a little bit of background about this problem or the idea of why we started this project. So we have a special type of bacteria, which are called vancomycin-resistant enterococci. And the problem with these bacteria is that they are resistant to antibiotics. So, if you get an infection, there's a high risk for you to die. And the mortality rate, as you can see, is around 30%. And for example, in 2019, we had 200,000 deaths worldwide that were associated with that type of material. And the hospital that we are working with, so that's in Germany, also where our university is located at, they have the problem that they have outbreaks of these bacteria inside of the hospital. So these are nosocomial infections. And of course, the patients, which are already like a vulnerable group, they have a high risk of dying. So, I mean, would be good to prevent or at least to slow the outbreak. And each patient that we can prevent from getting an infection is like a win for us. So, if we look at the transmission pattern, we can see that it mainly is transmitted by direct contacts. So the good thing would be if we know those patients, or if we can identify those patients that might be infected, we can isolate them so other patients won't get an infection. But the problem is, in practice, nobody knows who has an infection because there are no fixed screening criteria, and not everyone can be screened because of resource limitations. And this means the infection prevention control staff, they need some, let's say, tool to get like a warning for patients that have a high risk of infection so that they can select those patients that they want to screen. What we can use to model all of that setup are graphs and graph neural networks, because they are frequently applied in these epidemic domains and virus outbreak modeling domains. So, for example, also for COVID-19 modeling, they used such approaches. To summarize the idea, first of all, so the overview, we have all that structured data. So this first approach, this first case study that I want to present is only based on structured data. And we want to model the structured data in some way that represents all that information that we have, feed it in some model, or train a model on that data, and finally get, let's say, predictions or let's say estimations for patients at high risk. So that's our goal for this first project. And what we did was we curated our own data set, because usually you don't have access to that detailed data. And that's of course a problem. And as I said, we want to represent all that information inside of a graph, because graphs are well suited to represent these spatial relationships. And the main information unit, or the most important information unit for us to predict these high-risk patients, are the patients, of course. So patients are one node type inside of our graph. And for the data set that we used, it was about 1/3 of the patients that were hospitalized in that year, and in 2019, so before of COVID-19, to be kind of representative and not be like somehow biased by COVID-19 measures. And that makes around 8,000 patients that we had in our data set. And of course, also what we needed were the movements of these patients to know who had contact with whom, and also like in which areas of the hospitals these patients were located, to track their movements and their where they met. And these movements will present the edges in our graph. So like the relationships between patients, for example, or between the spatial units of the hospital. And in our data set, these were around 126,000 movements. And of course, to complete this graph, we also need the hospital information itself. And in our case, we have 150 organizational units, which can be like surgery rooms, examination rooms, stuff like that. And we also have the wards and the rooms that are linked to these wards, and the beds that are linked to these rooms. And these are also node types in our graph. So that's first of all how we want to build the graph structure. And we of course also want to use all that structured information that we have about the patients, so diagnosis, procedures, blood test results, stuff like that, to add more expressiveness to our model. And so the things you see on the right, these are the data sources that you can use for that. And also what's very important for the training of labels, and we get these labels from the microbiological result database of the hospital. So the main source of input data for the patient nodes, so let's say feature vectors for each of the patients, are very basic values. So for example, basic patient information like the age, the gender, also binary values or scale values or index values that are available in the database. And of course, also the diagnosis, surgeries, and so on. So all that information that we have, that structured information that we have in the hospital information system. And the relational information also comes from that database. That's the one that I presented previously. So for example, the room a patient was located in or the bed a patient was located in and so on. So that's also the information we get from that database. We also have, as I said, blood test results. So that's mainly what falls on the clinical chemistry data. And for training the model, we of course need the labels. And I mean, we don't have labels for all of the patients. We will use all of the patients to build our model because that's all the context that we have, and we don't want to leave out any context. But to run the predictions and to train the model, we of course can only compare it to actual valid information. So we will only train it on those patients that we have labels for, and labels in our case are swab results, for example. So those swabs that were performed for patients, and we know either if a patient is negative for some specific point of time or if the patient was positive during that time. So the labels we're using are the VRE results, so that specific bacteria I mentioned previously. But of course, we can also change the labels. So there are a lot of different microbiological findings in that database, and we can use the same data setup and the same training approach, but just change the labels. So I mean, it's transferable, the model in theory. And then we of course can predict whether a patient is more likely to be positive or whatever. To summarize, like the idea, I mean, Radu talked about graphs in his presentation. Here you can see another graph. We have all that information now linked up in this graph. So the spatial units, so wards, rooms, beds, organizational units, and also the patients. And in case of a patient being positive, we can track the risk for patients that have or probably have a closer or had a closer connection to that patient. So you can see that these patients down here, these two, point is at a different position. So here, they have a higher risk of having an infection than this patient, for example. And I mean, this becomes, obvious from just this little example. So if we now look at our real data set, this is a plot from our real data set, and there are no patients in yet. So this is only the data, the spatial information that we have. And what you can see is that we have some clusters in the graph, and each of that clusters is essentially a ward. So you can see that we have like wards, and each of these wards has like rooms connected to it, and each of these rooms has like beds connected to it, and we have these different wards in the hospital. And now if we bring in some patients, this gets a lot denser. So we have all that information now linked up in a dense graph, and we can track that information and finally then train our graph neural network on that graph. This is only the information for one day. So it's like a random day from our data set, but it gives you an idea about how our data looks like. The problem now with that setup is we have the spatial information and we know that these relations between patients and the hospital, but we don't know anything about the flow of time. So I mean, that's another dimension that we need to consider, because if we model all of these patients inside, so the whole year, the data set of the whole year that we have as one graph, there are, for example, patients located in the graph that were hospitalized in January, along those patients that were hospitalized in December, but there probably was never an encounter between these patients. So what we need to do is we also need to bring in the temporal dimension. And what we are doing is we will just, and this is quite popular and also very effective approach, we will just bring in a new set of edges, temporal edges, to link the graphs between days. So we can create a graph for each day, which is like the spatial information that we have, and then we can link the days per graph over time to bring in the temporal information. So that's essentially what I want to show here. So instead of predicting this information over the whole year, we will predict it on a daily basis and get like a risk estimator for each day then. Yeah, and if we do that, we can see that, gets a lot denser because we have much more information in that graph now. So this is, for example, a graph that represents 2 weeks, so we cannot really see anything anymore. But so that's all of the information that we now model. So we have the spatial information, we have the patient features, and we have the temporal information. And now we can train our model on that. And the model we are training is like a simple graph neural network that can operate on such data structures. And it is trained on these labels that I introduced earlier. So those labels that we got from the microbiological database. So and what we found in the end was we were able to predict the infection status of a patient with an F1 score of 0.88, so which is like really good. And also the people from the hospital, they were really impressed because they said, if we can only identify a few patients that have a high risk of having an infection, and we can prevent not the whole outbreak, but at least prevent it from spreading a bit, that helps us a lot, because it's also very expensive for the hospital if somebody has an infection, because they have to pay it, because it's like their fault, essentially. So maybe just a few words about this table. The static model is the approach where we model all of the data that we have from the whole year in one graph, so no temporal information. And the dynamic model is also includes these temporal edge sets that I just introduced. And we can see that time is very important. So this temporal dimension is very important, which makes sense because if we present patients inside of the graph that were hospitalized in January alongside patients that were hospitalized in December, that does not really make much sense because they didn't meet in reality. Yeah, so that was essentially the first project I wanted to present, the first case study. So based on structured data, where we wanted to support clinical decision making, and as I said, also in the beginning, improve patient safety. But we also have all these data, the unstructured data, and the second case study focuses on that information. And the title of this second case study is MedNuggetizer. So that's a little tool we built to process unstructured data. Well, the problem in this case is LLMs are increasingly adopted, as in any other domain, I guess, also in the healthcare domain, to process unstructured data. So we are also, we are working with the hospital that is linked to our university, and we are working with different groups there. For example, an infection prevention group and also like a urology group. And people from urology are using these models to extract information from clinical papers, for example, or from systematic reviews, stuff like that. So everything that they would usually read on PubMed, they throw these papers, or also these guidelines that I presented earlier, they throw that into some LLM and they want to extract information. But the problem is, these LLMs are, even if you use it with a parameter, a temperature parameter of 0, especially the reasoning models, are not 100% reliable. So that means we have some variance, and the problem is variance is not really optimal in the medical domain, because we want to have the findings as reproducible as possible. So what can we do about that? That's where we introduced, that's why we came up with this tool. And it's the screen is a little bit small now, but I want to talk about some of the parameters that we have. It's not that much. We essentially have 4 fields. The first one is just like a PDF upload, so they can throw in their guidelines, their medical papers, their systematic reviews, whatever. And then they can also issue a query. So that's the second field. And now to bring in this confidence of the LLM extraction process, we also define a parameter n, which defines the number of extraction runs, repeated extraction runs. And we also define a confidence parameter. So how often in all of these extraction runs, a specific information nugget must appear to be retained as high confidence. So that means we can repeat the information extraction process a number of times, and only if the information nugget appears, or if specific information nuggets appear a specific amount of time. So let's say if we run it 5 times, an information nugget must appear 4 times to be retained. Otherwise, we just discard it because we can assume it's not really that high confidence because it was only identified 1 time and not at least 4 times in these 5 runs. Here's just a real quick example. I will also present a more structured evaluation of that tool in a second. So we have that paper here. So just one paper that we will upload to our tool. And we also have that query, which is an urology use case. So that was developed in cooperation with the urology group. And we will now run the extraction of information nuggets 5 times, and only those nuggets that appear in 80% of the runs, so the extraction runs, which means at least in 4 runs, only those nuggets will be retained. All the other nuggets will be discarded because we don't have that extremely, or let's say at least higher confidence of being actual relevant information nuggets. And then our tool is like running through this process. Maybe what I should mention, so that's only for one PDF file now, but if the user uploads multiple PDF files, we also run clustering over the nuggets that were identified across files to only retain those nuggets that have a high confidence across multiple sources and not only from one source. So we have like an iterative clustering process to be confident within a document and be confident across documents. So that's the idea of the process. And then, I mean, only had like 4 nuggets left. We have these clusters of nuggets, and we have these high confidence nuggets that the user gets, and then they can do whatever they want. They can use that knowledge to, for example, decide on the treatment they want to do, or they can use that knowledge to perform a more structured search after that. So it's like an input for a structured query, things like that. And I mean, the interface is very simplistic, but it's like the important thing about that tool is like the back-end process, which is based on strategies that we use from, I don't know if anyone knows the Ginger framework, which was introduced at CGIAR I think it was this year. So essentially, the information nugget extraction process is based on that framework, and we make this IR technology available and easy to use for medical professionals. And to evaluate whether this information and these extracted nuggets are actually relevant, we performed an evaluation. So we had this use case that was again proposed by the domain experts from urology. And as an input, we now didn't use not only one file, but we used 4 of the major guidelines that these that experts use. They also identified 10 recent PubMed indexed articles that are relevant to them, and also 4 randomized control trials. So it was quite a big number of PDF files. And then we were running our process and like this pipeline over the documents with 5 repeated runs for each file and clustering confidence of 80%. So at least 4 of the runs should contain this information nuggets. And then the human experts, so the urologists, they annotated all of the resulting nuggets and all of the resulting clusters for, first of all, consistency of the cluster. So are these clusters in the end relevant, and also for the relevance of the nuggets. And what we can see is, so it was rated on a Likert scale from 1 to 5, and 5 is the best value. We can see that they were really satisfied with the outcome. So for the clusters as well as for the nuggets. So we have very high Likert scale rating. And we also identified a large number of clusters and a large number of nuggets, and it seemed that they all were relevant to the experts, and they now can use the underlying IR technology, and we provide this easy to use interface, and it is also available open source, so the code that we wrote for that. So this is essentially the evaluation results for our this second case study. And to conclude and present a take-home message for these two case studies. First of all, what you did see now was in the first case study, we had graphs to capture the context of the patient. So the spatial information, the temporal information, the structured data that we had as an input, and represent that context in a graph. And in the second case study, what you saw was we tried to capture the context of the knowledge. So basically all of these documents, guideline documents, clinical research papers, stuff like that, and used large language models and clustering to capture that information in the second study. From a technical perspective, what we can identify as takeaways or take-home messages. First of all, to represent complex relational information in the healthcare domain, graphs and graph neural networks are suitable. I mean, this is not really novel, but we confirmed this in our case study. And also to mitigate these LLM hallucinations, or maybe not only hallucinations, but the problem of LLMs being non-deterministic. We can use repeated runs and clustering to make the outputs more reliable for in the medical domain. I mean, we can use that for every domain basically, but in the medical domain, it's especially important. And what's also important for us, we don't want to replace the actual experts. These systems, so both approaches are designed in the idea is to use it in a human in the loop way. So the patients are informed by our system, but they are not replaced by our system, and they can use that information to, make informed decisions, but they don't have to rely on that information. So it's just like a tool that helps them in the practice or in like the clinical practice. As I said, the implementations for both of the case studies are open available to the community. So the outbreak detection code, not the data, of course, but the code is available via GitLab. So it's the Open Center, and the code for our tool is available on GitHub. So you can download it and extend it and label it or whatever. And also, like the first case study that I presented was published in Global Digital Health. So if you want to read more about it, you can also have a look at the paper. And I don't know if it is possible to share the slides afterwards, but maybe you can upload the slides somewhere, and then you can also check it out.